Hello and welcome back to the lab. So we're continuing work on the 3443 plug-in today for the 3440A digital voltmeter. The capacitors that I ordered have come in, and you can see that the new replacements are quite a bit smaller. It's about This is a 10 microfarad at 25 volts. Seems to be about maybe a centimeter shorter. Here's the new 10 microfarad at 150 volt replacement capacitor. It also seems to be about a centimeter shorter than the original. Um, I'm trying to use the metric system here. I actually use inches and stuff in my country, but I realize that there's a lot of international viewers, so I'm going to try to use the metric system when I can. Um, just as a side note, I remember one time I was mentioning in my video that my spectrum analyzer was about 90 pounds, and one of my viewers commented that it was very inexpensive for such a fine instrument. And I was like, gee, I never mentioned the price. Why would you think it was inexpensive? And he thought that 90 pounds was the price, when I was really trying to say that the mass of the instrument was about 41 kilograms. I should have just said kilograms from the very beginning instead of saying 90 pounds. Then there wouldn't have been any confusion. So I'm going to try to do that when I make my videos. I'm going to try to use millimeters and centimeters and so on and so forth. But that may not always happen. So we'll see how that works out. So anyway, um, somebody asked me how I knew that this capacitor was defective. And so I'd like to show you on my Octopus curve tracer how I identified this particular 10 microfarad capacitor as being defective. So let me focus the camera on the curve tracer, on the scope that's connected to the curve tracer, and we'll take a look at these two capacitors here, the good one and the defective one, and we'll make a comparison. Okay, so we're looking at the screen of the Octopus curve tracer on the scope that's connected to it, of course. So we are displaying voltage on the x-axis and current through the component under test on the y-axis. Now, when I put the test leads of the curve tracer across a good 10 microfarad capacitor, this is what I see. It's an oval shape because there's a phase shift between voltage and current through a capacitor. So that's why you have this oval shape in the capacitance. Now, a higher value capacitor will be narrower and stretched out more vertically, and a lower value capacitor will be shorter and stretched out more horizontally. But in each case, it's oriented in this fashion. Now, here is what the defective capacitor looked like when I connect the curve tracer to it. You can see that it has an oval shape still, so it means it is a capacitor, and it seems to be about the right size, but it's tilted diagonally. That means the current is in phase with the voltage, and that implies that it's resistance. There's a resistance both in series with this capacitor and across it as leakage in this capacitor. It is a defective capacitor. So once again, good, bad. So that's how I knew that this 10 microfarad capacitor was defective. Okay, so one of the 10 microfarads, the 10 microfarad 150 volt capacitor that I replaced was this one under here. And once I removed it, I cleaned up all the stuff that had leaked out of it with a Q-tip swab and some isopropyl alcohol. I made sure to clean up everything all around because that stuff can be corrosive and eat up what's left of your circuit board if you don't remove all of that stuff. Plus, it's conductive as well, so you don't want it shorten things out. So that's the 150 microfarad, 150 volt, 10 microfarad capacitor. I had to remove the zero pot from the front panel and to move it out of the way. So I also had to loosen the range switch and slide it over to one side. I couldn't remove it because it bumped into the chopper block assembly, and so I couldn't actually remove the range switch. But just loosening it and removing this potentiometer shaft gave me enough clearance so that I could get in there with my soldering iron and desolder it from the top of the circuit board. Now, I like to use my solder sucker desoldering tool, right? But it, the I couldn't get in there. It was too fat to. I didn't have clearance to get in there with the solder sucker. So what I did, I came up with a solution to that problem. I took a piece of heat shrink tubing, attached it to the tip of my solder sucker, shrunk it down so that it was a nice tight fit and didn't leak any of the vacuum, and it extended it by about 2 centimeters, I guess, and got in there with that way. It gave me just enough clearance so that I could desolder, remove the solder from that connection on the far side of the electrolytic there. So that's the one that was leaking, but it actually still tested good, that particular 10 microfarad. But I decided to replace it anyway, of course. This is the one that we just looked at with the curve tracer. And that was also, I replaced it from the top and cleaned up around it, cleaned the solder flux and so forth around it. So those are the two components that I replaced on this circuit board. Some people tried to suggest that I should replace all the electrolytic capacitors. If this was a customer's instrument that I was working on, that's exactly what I would do. Replace all the capacitors while it's here. There's no point in changing some of them and then having the instrument come back in a year with more failed components. Might as well, while it's here, since I already have the capacitors in my hand, I might as well just put them in and replace them all. But because it's not a customer's instrument, it's actually my personal instrument that I will plan to use here in the lab. I I'd like to only replace the defective components and leave the ones that are still good, leave them as original as possible. There are a couple of reasons I can do that. I want to do that. The main reason is because it's less expensive, of course. It's certainly less expensive to only replace the defective components and not everything. But and one of the other reasons is that because it's my personal instrument, I'll be using it, so I will notice right away if another component fails. I will notice it right away and be able to work on that problem right away, right here, because it's never going to leave this lab. But the most important reason why I don't change components that are not defective is because the reason I'm working on these is because I want it to be a learning experience, not only for myself, but also for my viewers. I want to understand what the failure modes are for the parts that do fail, instead of just randomly shotgun replacement of every component just because it's here and I can. I don't learn anything from doing that except how to solder and unsolder, which I already know how to do. Um, but if I learn how to troubleshoot and isolate problem failures to specific components, I've actually learned something, and that's the value I get from these instruments. So that's why I do that. If it were a customer's unit, I would most likely replace all the electrolytics, whether they were good or not good. But because it's mine, I'm not going to do that. Um, I still have them all available. I can replace them at the later date if I need to. So let's put this instrument back together. And also wanted to mention that I was planning on replacing the neon light bulbs inside the photochopper assembly, but I have not done so yet because I'm not sure that they're actually defective or weak or in any way causing a problem. I still have them available and I can drop them in if I want to do that. But I left the original ones in there for now because it seems pretty likely that they're still okay and there's no point in swapping them out for the same reason we talked about just earlier. So let's put this plug-in back together. Drop this board down and screw the top in over here, and we'll plug it back into the mainframe and see if we have fixed the instrument, solved the problem. Maybe. I hope so, but maybe not. I don't know. We'll find out. Okay, so let me show you what just happened. I put the plug-in back in the mainframe, all right, and I turned it on, and I'm getting ready to make some adjustments. And one of the adjustments is on this little 10-turn trimmer pot right here. And while I was making the adjustment, you're supposed to put 8 volts on the input and adjust this pot right here for exactly 8,000 counts on the display. And I was getting close to 8,000 counts when all of a sudden it went to 9,400 and something counts, and it stayed there. And nothing I could do with the pot would make any difference whatsoever. Turns out this pot failed while I was adjusting it. The little wiper contact on that pot opened up completely, so it was at its maximum full resistance value all along, and you couldn't make any changes to it. Now, it's a little 10-turn trimmer, 60 years old, and it's completely sealed up. There's no way to like clean it or repair it or anything like that. Here it is right here. Here's the one that actually failed. As it turns out, some of you probably already know, if you look behind my picture in the profile picture, in the profile photo at the top of this channel, you can see that I do own another 3340A digital voltmeter. That picture was taken long before I purchased this instrument, and you can see one of these in the background behind my photograph. So you should know that I have another one of these instruments already. It's not a parts donor unit. It's a working instrument that I actually use. But for right now, it's a parts donor unit. I took the trim pot out of that instrument and put it in the one I'm currently working on, replaced it. So here's the defective one. It's a 2K trimmer, 2 kiloohms, 10 turn. And it's always 2 kiloohms now because the wiper does not make contact with the resistive element at all. And so it's just completely open. So it's at its maximum value all the time, and there's no way to kind of repair it. So I had to steal one out of my other working 3440A. I will be able to order a replacement, although the modern ones are a different size and shape, and they won't actually be a direct fit. I'm going to have to finagle the wires a little bit to get it to mount in the circuit board, but I will be able to replace this one in the other 3440. So that's what I'm going to do. But in the meantime, I have this one stolen out of that unit and placed it into the unit that I'm trying to work on right now. I still don't know if the plug-in is repaired or if it's not repaired, but at least we got the mainframe part working again. All right, so it's about a week later, and over the past week, I've spent countless hours working on this 3443A plugin and making very little, if any, progress whatsoever. I'm starting to lose confidence in whether or not I'll be able to get this thing repaired. But in that time, I was able to locate an exact replacement, exact size and shape, and exact pin out and pin spacing and so forth for the damaged defective trimmer, 10-turn trimmer. I guess it's actually a 12-turn trimmer potentiometer for the problem that was in the mainframe, not in the plugin, but it was in the mainframe. So this is the defective one, and here is the replacement trim pot. So I'll be able to stick that in. So let's do that now. Well, this is the board where that trimmer pot goes on, and I have removed the defective one. And in fact, I removed the temporary replacement one. These are the 3 holes. Now, if you look closely at this hole, you can see that the pad has come off the PCB. Um, it's like every time I touch this thing, something else goes wrong. Um, the plated through hole is still there, so I should be able to solder it just fine. But the little circle pad has come off. I guess my soldering iron has too much heat for these old delicate circuit boards from the 1960s. This doesn't often happen, but it happened this time. We're just gonna have to work with it. Okay, I've inserted the trimmer on the other side, and now we just solder the 3 pins. And hopefully get this one, at least the mainframe portion, back up and in operation. Hopefully that one with the missing pad has made a good solder connection. I'll check it with my ohm meter to make sure. All right, so there's the replacement trimmer capacitor, trimmer resistor. It's a couple millimeters longer than the original. Um, the original one was just like this one, but here's the replacement. It almost bumps into this transistor over here, but there's enough room. It's a perfect fit. Okay, so the board is back in the instrument, and it has warmed up for a considerable amount of time. I don't know, 15 minutes, 20 minutes. And we've done some preliminary adjustments. These adjustments back here are for the 0, and you cannot really access them unless you remove the plug-in. So without that uh, extender to pull the plug-in module out of the instrument, I have to pull the module out, make a small adjustment, put the module back in, see how my adjustment has affected the reading, and continue that iterative process until I've got 0 on the front panel. It's very time consuming and very difficult, but we managed to do it. Okay, so now we have 0 on the front panel with a short on the input, and they want you to apply 8 volts on the 10 volt range, of course. And wow, it's quite a bit off, but hopefully we can adjust that for 8 volts. Hopefully. And there we go, 8 volts. Beautiful. Now you're supposed to check for negative 8 volts. Off by 2 counts. Even though it reads 0 with a short, it's off by 2 counts between positive and negative. I'm not sure what to do about that. We're going to have to do it, maybe compromise with this. Make it 7.9. Let's try something like that. Yeah, it's still off by 2 counts, but that's okay. I mean, that's about as close as we're going to have to go with it. There may be some small amounts of ground current or something going on here. I don't really know. But it's off by 2 counts, even though it still reads 0, I imagine. Yeah, it reads 0 with a short on the input. But the positive reading and the negative reading differ by 2 counts. We're close. We're close. Now, what you're supposed to do is this other pot, you leave it in the negative 8 volts, and this other pot over here, You're supposed to adjust the accuracy of the internal calibration. So when you push this button, it should read also the same. It should read 8,000, but we're going to make it read 79.99. I push the button, it does read 79.99. You make sure that turning this pot makes a difference. It certainly does. All right. Okay, so the internal 8 volt, negative 8 volt calibration reference voltage matches my external 8 volts input. They both read 79.99 plus or minus 1 count. All right, so the mainframe is now working again, but the plugin still is not. But we're getting closer. All right, so against my own repair philosophy, I decided that because I did have the values of these electrolytic capacitors in stock, I decided to go ahead and, even though earlier I said I wasn't going to do this, I decided to go ahead and just replace them all. So I replaced 1, 2, 3, 4, 5, 6, 7, 7 of the electrolytic capacitors. This one and this one I did not have replacements for, so I did not replace them. Those replacements seem to maybe make a small change, but really not a significant change. So I don't know if it was helpful or not, but at least we have new electrolytics for most of them in there now. I'm starting to get a little bit desperate. So let me show you one of the things I noticed. I noticed that all of these transistors had been previously unsoldered and resoldered. I assume that that was because the previous owner must have removed them to test them out and see if they were good. But I wanted to make sure that he replaced them with the correct ones, because I've had instances in the past where I bought these old instruments and someone had put the transistors in the wrong positions or something like that, or they used incompatible transistors and threw off the entire circuit. I assume that probably wasn't the case here, but I just wanted to double check that. When doing so, I noticed that I think it's this one, the Hewlett Packard model number on this transistor Q, this is Q5, um, did not match the transistor part number that was in the manual. Let me show you that. I've already scribbled in a chicken scratch for the correction, but in the parts list, the replaceable parts list in the back of the manual, section 7 of the manual, for A2Q5, says the part number is 18540023, and that it's an NPN silicon transistor. But on the schematic, that transistor is right, where is it? Right here. This transistor is actually not used as a transistor. It is used as a reference diode with a forward biased voltage drop from base to emitter, and it should be 0.3 volts here. Explains in the troubleshooting that there's no connection on the collector and that the base to emitter drop should be 0.3 volts, which implies that it's a germanium transistor, not a silicon transistor. And also, if you look at closely, the arrow is pointing in, which means it's a PNP transistor, not an NPN transistor. So it is a PNP silicon transistor. I mean, PNP germanium transistor, not an NPN silicon. So the part number in the parts list must be incorrect. And I went to this manual changes sheet that's in the back of the parts of the manual, and I found it. Errata. And they made a mistake in the manual. and they want you to change HP part number of A2Q5 to 1850-0062. Now 1850 parts that prefix with an 1850 are germanium transistors. They're not silicon transistors. And this particular one happens to be a PNP germanium transistor. So the part number that is actually soldered into the chassis of the instrument, onto the PC board of the instrument, onto A2Q5, is this part number, 1850-0062. So that means this is the correct part. So I just wanted to make sure that on my instrument, this is the correct transistor, and in fact it is. And if you test that transistor, it turns out indeed to have a 0.3 volt base to emitter forward bias voltage drop, like a germanium transistor should have. So this transistor is good. And in fact, it's not even used as a transistor. It's simply a germanium diode with a forward bias, used as a 0.3 volt forward bias reference voltage diode. So, and I checked all the rest of the transistors as well. Each of them are the correct part number. So the previous owner did a very good job in actually unsoldering them and resoldering them, and they all test out good. So all the transistors in this amplifier circuit are good. All of the capacitors, with the exception of this one over here and this one over here, have now been over here. You can't see it, but that one down there have been replaced. Those are the only two electrolytics that still remain that are original. The symptom I'm seeing now is that on the 100 millivolt and 1000 millivolt or 1 volt range, you cannot get the adjustments for these two trimmer pots. You do not have enough range to bring those two ranges into spec. I considered changing some of the precision resistor values to change the gain of the amplifier circuit and do some modification to it that way, so that these resistors will bring those calibration measurements into range. But I also noticed that the measurements on the 1000 volt and 1000 millivolt and the 100 millivolt range are not repeatable, that they jump around a lot and they don't remain correct. So at first I thought maybe these resistors are dirty, the adjusters, the trimmer pots are dirty, the wipers may be contaminated or something. So I hooked them up to my ohm meter and measured them while turning them, and they do sweep smoothly through their adjustment range. So they're not dirty. They're not the cause of the noisy and inaccurate measurement reading. In fact, these trimmers, in conjunction with these red colored precision resistors, define the gain of the amplifier to make it measure accurately. And if I just use an ohm meter, I can adjust these trimmers along, which are in series with these red precision resistors, to make them precisely measure the resistance value that's needed to cause the proper gain. This pair would be 900 kiloohms, and this pair would be 90 kiloohms. When you put those two together, you get 990 kiloohms, right? You can measure those, and they are exact because I adjusted the trimmers to make them measure exactly 900K and 90K. So there's nothing wrong with that part of the circuit. So here's what I finally realized. It could very well be that these reed relays have dirty contacts. There's no way for me to measure it while it's energized and plugged into the mainframe. because I don't have the extender card to extend the plug-in outside of the frame of the mainframe. So I can only make measurements of them open to see if they do open. And I took a small, powerful magnet and tried to close the reeds in the relays with the magnet and measure them when they're closed. And when I do that, I measure that they are uh, reading not 0 ohms. Sometimes it's a kilo ohm, sometimes 100 ohms, sometimes 10 ohms, sometimes 50 ohms. Certainly not repeatable, and certainly not a complete short in all of these old reed relays. So there are 5 of them, and I'm like, well, I don't know, but perhaps, or actually, there are 6 of them, but perhaps that is the entire problem. So here's what I did. This relay right here um, controls the gain of the 1,000 millivolt range, the 1 volt range. They call it the 1,000 millivolt range. I took my jumpered across the relay like so to make sure that it closed completely. Tucked the wires in carefully, closed the plug-in up, and plugged it back into the instrument. And suddenly, my instrument is working perfectly fine. The problem with this instrument was the reed relays, the reeds in the reed relays all along. Now, the question is, can I find replacements for those particular sets of reed switch contacts for these reed relays? And I can, and I have found a replacement supplier for those particular set of contacts, and I placed an order with them. So when those contacts come in, I will try to carefully unsolder these reed relay coils and the contacts from the circuit board, replace the contacts because the coils are all fine, and the logic that drives the coils is all fine as well. It's just the contacts are 60 years old, and they don't have, they have some resistance to them now. So when those come in, we'll be able to complete the repair of this particular instrument. I hope, at least I hope, but it means one more episode, unfortunately. So that will have to do it for this episode of the HB3440A repair. And please like and subscribe, and stay tuned for part 4 of this voltmeter repair, when in fact I hope to actually get the entire instrument working and up to meet all of its specifications. Thanks again for watching.